Hello, welcome to Internal Combustion Engines Presentation. We are Section 8, Team D. Our team members are Christopher Song, Wesley Lackey, Eric Salisbury, and I am Itai Sandy. In this experiment, a generator is constructed based on a sectionalized internal combustion engine. We were requested to model the system parameters and control. The main instruments used in this experiment were an encoder and a force transducer. The encoder was used to detect the engine and motor shaft position, while the force transducer was used to detect the engine torque. The system is powered by compressed air, but it can also be operated on propane. To start the engine, a 48-volt regenerative motor is used to turn the engine. The same motor can also be turned by the engine to generate energy which is stored in a battery. The goals of this experiment are to identify the system parameters, control, as well as optimize the energy output. This was done by calibrating the force transducer first with known weights, measuring the arm length as well as the voltage from the sensor. The second step was to determine the internal combustion engine mechanical properties, which are the frictional torque and the flywheel inertia. This was done with the engine head off and no air injection was used. Also, in the second week, we characterized the full four-stroke cycle of the engine, this time with the engine head on and with no air injection used. The final part of the goal of this experiment is to model the engine output with simulated combustion, this time with both the engine head on as well as air injection. These are the goals for this experiment.
To meet these goals, we want to first take a look at the ICEngine outline. By dissecting the model and starting with the basic equation of work, we can isolate all of the variables that need to be experimentally calculated, solved, or measured from the work done on the flywheel. Starting the first week and lasting the duration of the experiment, a force transducer and a torque sensor are used to take torque measurements for torque calibration. Following this calibration, an engine head is placed on the ICEngine with no pressure for measurements of the no pressure subsystem. Lastly, a new engine head with applied pressure is attached to record final measurements of the entire engine in full operation. To calibrate the torque sensor, measurements from the torque sensor in union with the force transducer are needed to create a calibration equation. From this data, torque calibration gain and torque calibration offset are found and used with given variables to complete the final calibration of the sensor. To further dissect the ICEngine model, after measurements are made, we need to solve for the unknowns given in the previous outline for the work done on the flywheel. These include the work of friction, work of the piston, work due to air, the moment of inertia, and work done by air. To complete these calculations, the forehead assumptions on the right are made to isolate parameters and control the system. Multiple operations are required in finding these unknowns. The first method includes measuring values directly from the lab equipment. These measurements help solve for motor work. The next method is integration. By integrating torque, pressure, volume, and angular velocity, we find key variables that are included in formulas for the unknowns. The last method is iteration through the outline. By reverse engineering through each input in the model, key terms in the work equations can be simplified.
So this is our work energy model, and so here's our force transducer calibration and uncertainty. So this is our uncertainty for the, so this was part of our week 1 analysis with the motor, which
This graph represents the no flywheel motor analysis. Comparing this graph to the flywheel cases, there is more variability in the motor torque. Note that the frictional torque matches the medium setting of the flywheel case. This is expected as the motor setting was turned to medium.
So this is our week 2 motor analysis with flywheels.
The graphs on this slide represent the motor analysis with no flywheels. The graphs for the no flywheel case are similar to the flywheel case. While there are differences between the graphs, no conclusions can be made from the graphs alone. Within the 2 weeks, we met several deliverables. First, we determined the work of the motor. Second, we determined the work due to air. Moving forward, we look to model engine output with simulated combustion, write the report draft, update the work energy model, and optimize the work output of the battery.